complexity to it. Just like you have, you are you, but you have all this complexity to you, right? Extra detail. So every real number has extra detail to share. All right, welcome back to another video. Today I thought I would talk a little bit about imaginary numbers, complex numbers. There's a lot of curiosity, and this isn't typically taught in high school, even in university, unless you're in engineering, right, or math. So but let's talk a little bit about what I is, where it comes from, and then talk about this structure. And that'll be our sort of foundation, because I make a lot of videos on complex numbers, and if you don't understand what these are, then sometimes those videos fall flat, right? So first off, let's talk about this for a moment. This simply comes from the question, if I was to say to you x squared is equal to -1. Well, we have a problem here, do you see? Because what this is really saying is what number multiplied by itself would give -1, and there isn't any real number, okay? So what we do is we simply square root both sides. So we use our imagination here, okay? This is still a legitimate number. It's not a real number, it's an imaginary number. So if I square root both sides like you did when you were even in grade 8, right? When you were doing like Pythagorean theorem questions. So then what we do is we sort of use the idea that this number, we call this a number now. Square root -1 is a number. It's not on the real line, and we call it I because we used our imagination to come up with it. Okay? So this gets used whenever we run into that quadratic issue of a negative, right? You can't take the square root of a negative or even the fourth root of a negative in the real numbers, but you can in the complex number system. So let's keep that for now. We want to see that this substitution can always be used. Whenever you have a square root -1, you say I. Now what's this? Well, that's actually the form that the complex number takes. So you can see the first number here, A, that's the real number, just like any other number that you would know. But what we do is we add in an imaginary component or a complex component. So if I was to draw the x-axis is actually the real line. And all the numbers that are on that line are the real numbers, all of the rational numbers, all of the irrational numbers, all the numbers that you know from high school. So let's say, suppose I locate 0, there's 0. So if I make up a number, let's say I take z to be 5 plus 1i, okay? So I'm gonna use 5 and 1, which are both real numbers, but notice this real number 1 is attached to the imaginary number I. So what does that look like? How can I use it? Well, just to get our toe in the water, I start by graphing 5 on the real line because 5 is the real part. And I just walk 5 units over and I locate it. That's where 5 is. That's the number you've always known. Now, the best way to think about this intuitively is to imagine that every number that you know essentially has a complexity to it. Just like you have, you are you, but you have all this complexity to you, right? Extra detail. So every real number has extra detail to share. And the complex numbers provide that. So in other words, at this location 5, where x is 5, I can draw a vertical line through it, which is not the y-axis, okay? It's the complex axis. And then I can hover above or below that line, okay? And so in this case, it says go up 1. So that's like using the ordered pair, 5, 1, where 1 says go up 1 unit. Well, 1 unit is I. So I count i's, 1, 2, 3, and I could go down i's. So that means that if I go up 1, that's 1 I. And that number right there, I'm going to bullet it in. That point becomes a representation, a geometrical representation of the complex number 5 plus 1i. And if I were to draw in the general axis right here, that's the general axis. I'll call it the complex axis. When I combine the real axis with the complex axis, I get a diagram called the Argand diagram. The Argand diagram. And this sort of gives us the basis of looking at complex numbers in different ways. This is called the Cartesian form, where you're just using ordered pairs to plot them. But just to motivate another idea, if I look at the distance that is from the origin, it looks a lot like a radius, right, in trigonometry. And if I was to drop a perpendicular to the x-axis, it's really feeling like trigonometry. This side is 5, that's 1, and you could then use the Pythagorean theorem to determine that distance. It's called the modulus, and I could also figure out what that angle of rotation is using some trig, basic trig. That's called the argument. So often you'll see complex numbers not written in Cartesian form, but something called polar form. So the same number z could be written as, well, r is the radius, it's the distance from the origin, multiplied by, I'm going to sort of jump a little bit over the moon here, cis theta, where theta is the angle of rotation like you did in trig. So the modulus and the argument define that. So every Cartesian form could be written in polar form and vice versa. Just to end this, I will tell you this, since if you're still watching, you're still curious. The C stands for cosine of the angle, okay? And plus I, well, I makes its way in there because there's complexity, times the sine of theta. And I have some videos already using cis theta, and I'll make a small sort of foundational video for you guys just to get used to using this, because they're actually quite fun. And there's a lot of really cool math that you can do using them. So that's sort of a little basic, put your toe in the water on complex numbers. If you like the video, don't forget to put a like on the video. Subscribe for a lot more videos to come.